Hey everyone, and welcome to today's Explainer. We are looking at a truly fascinating and honestly game-changing development in the world of artificial intelligence in healthcare today. Right now, large language models encode an unbelievable amount of medical knowledge, but when they are actually asked to step in and diagnose a real patient step by step, well, they hit a massive bottleneck. So today, we're exploring a brand new multi-agent framework called GraphDx. This research is fundamentally changing how AI approaches sequential medical diagnosis. It's taking it from, probabilistic guessing to precise, cost-aware planning. Okay, let's dive into this. Here is our roadmap for the explainer. We'll start with 1, the AI diagnostic dilemma. Then cover 2, the knowledge reasoning gap. From there, 3, enter the GraphDx framework. 4, the 3-agent architecture. 5, real-world benchmarks and backbones. And finally, 6, the future of AI agents. Kicking things off with Section 1, the AI diagnostic dilemma, specifically looking at the over-testing issue. So, to put it simply, why do AI doctors over-test? If you have ever worked with standard LLMs in any kind of constrained environment, you might have noticed they behave a bit like a highly anxious medical intern. When they're put under pressure to make a tough diagnosis, they panic. Instead of using logic to carefully narrow down the options, they just order every single test in the book, just to be completely safe. Actually, this quote from the research hits the nail right on the head. The model knows the facts, but lacks a mechanism to weigh diagnostic relevance against resource expenditure, resulting in defensive medicine. Current AI models basically default to high recall strategies. They want to grab absolutely all the information possible, mostly because they just don't understand the real-world cost of a blood test, an MRI, or an overnight ICU stay. And that inflates healthcare costs and completely ruins the interpretability of the AI's decision-making process. Moving right along to Section 2, the knowledge reasoning gap, or failing at logic. So the crucial point here is what researchers call the knowledge reasoning gap. This happens when an AI holds extensive factual knowledge. It's like having memorized every single medical textbook ever written, but it completely fails at systematic reasoning under cost constraints. It just defaults to probabilistic next token generation instead of logical step-by-step sequencing. And here's what you really need to take away from this. Standard prompt engineering cannot fix this. You can't just tell the AI in the prompt to be more careful. LLMs are architecturally optimized to generate text, not to perform cost-aware planning. Which brings us to Section 3. Enter the GraphDx framework and the shift to deterministic planning. If standard LLMs act like those anxious interns relying on probabilistic guessing and text generation, GraphDx acts like a seasoned, experienced attending physician. It does this by leaning heavily into deterministic planning and evidence scoring. GraphDx explicitly separates the act of generating language from the act of strict logical sequencing. It doesn't even try to do both at the same time. The absolute foundation of this entire system is the Automated Medical Diagnosis Knowledge Graph, or MDKG. Standard knowledge graphs usually lack the hard quantitative data needed for decision-making, but GraphDx builds a graph with some very specific properties. It includes quantized typicality for symptoms, meaning it knows exactly how mathematically common a symptom is for a specific disease. It uses an action-centric topology that maps specific tests directly to diagnostic pathways. And most importantly, it assigns dual objective attributes to every single edge of the graph. It scores both its diagnostic relevance and its real-world cost. It essentially transforms unstructured medical knowledge into a pure deterministic planning surface. Let's move to Section 4 and see how this builds the 3-agent architecture, focusing on agent specialization. When GraphDx processes a patient scenario, it actually splits the responsibilities to prevent reasoning drift. Step 1 is the perception agent, which handles the natural language understanding and extracts symptoms from the patient's data. Then, Step 2 is the reasoning agent. Now, pay really close attention here. The reasoning agent does not generate text. Not at all. It acts purely as a deterministic planner on the MDKG, calculating optimal test sequences to minimize uncertainty per unit of cost. Finally, Step 3 is the decision agent, which takes that pure logic and translates it back into a clinical response and a final diagnosis. By keeping the LLMs strictly in perception and decision roles, the whole system is forced to respect those resource constraints. All right, Section 5, real-world benchmarks and backbones. Let's see how they actually proved GraphDx works. Now, what's really interesting about this slide is the sheer granularity of the data used to validate the framework. The researchers didn't just toss a few simple text queries at it. They tested GraphDx against the Mimic IV database, which is this massive, highly granular medical data set. The AI had to process complex, messy information across different modules: hour-to-hour vitals in the ICU, triage assessments in the emergency department, and lab measurements and microbiology cultures from the main hospital. This proves GraphDx can handle dense, chaotic, real-world clinical environments. And here is another absolutely crucial detail for any developers watching. GraphDx is not a new foundation model. It's a routing layer that sits on top of existing models, meaning its benefits are totally backbone agnostic. The researchers validated this framework using some of the most powerful models out there right now, including Llama 3.3, Kimi K2, and DeepSeek V3, which is this massive 671 billion parameter mixture of experts model, known for its incredible training efficiency. So no matter which powerful brain you plug into GraphDx, the architecture just makes it better. So what were the actual real-world results of adding this cost-aware planning layer? Well, GraphDx reduced unnecessary diagnostic test costs by up to 54%. That is a massive, game-changing reduction in wasted resources and defensive medicine. And this brilliantly illustrates the true power of the framework. You might logically expect that cutting tests by 54% would hurt the AI's accuracy, right? But the exact opposite happened. Alongside those cost savings, diagnostic success rates simultaneously skyrocketed, reaching a peak of 93% across the benchmarks. To put that in perspective, the baseline for standard models was just 50 to 68%. It turns out, when you force an AI to actually think logically instead of just guessing the next word, it gets the right answer faster and a whole lot cheaper. Finally, Section 6, the future of AI agents, looking beyond just healthcare. The overarching takeaway here goes way, way beyond just medicine. If you are a developer right now, and your current pipeline relies on a single LLM to manage state, recall knowledge, and make decisions all at the exact same time, you are actively reproducing the knowledge reasoning gap. Systems that mix probabilistic text generation with logical sequencing consistently drift when put under pressure. Separating language generation from deterministic planning, using specialized agents, is, for sure, the future of reliable AI in literally any constrained environment. Which leaves us with this final thought to ponder today. If separating language from logic can fix the AI doctor's overtesting problem and save up to 54% in cost, what other industries urgently need to adopt the GraphDx pattern? I mean, imagine deterministic routing graphs revolutionizing finance, supply chain engineering, or even legal compliance. The blueprint is right here. It's just a matter of who builds it next. Thanks for joining me on this explainer, and keep exploring.